Welcome to MrCScience.com's video on Gay-Lussac's law. Gay-Lussac's law is interesting in that it relates gases by volume with stoichiometric figures, much like we compared moles with stoichiometric figures. Now, the premise of Gay-Lussac's law and what was found is that 1 mole of, say, hydrogen gas has the same volume, or one mole hydrogen gas's volume equals 1 mole helium gas's volume equals 1 mole carbon dioxide gas's volume, etc. Anything with that is a gas, its volume for the same molarity or the same amount of moles will be equal. So what that really means is that in an equation such as, let's do the formation of ammonia. So if we take 3H2 plus N2, both gas, this is important for this, plus N2 gas gives us N2NH2, or 2NH3, sorry, 2NH3 gas. And what that means is we can compare volumes. So if we had 3 liters of H2, that would give us 1 liter, or reacting that with 1 liter of N2 would give us 2 liters of NH3. All these being gases. This can only work with gases. But instead of comparing moles, we can combine volumes. So let's say we wanted to create 5 liters of ammonia gas using the above equation. How many liters of hydrogen and how many liters of nitrogen would we need? Both gases. So start with what we know. We got 5 liters NH3 over 1 times. Now let's start with our hydrogen. We know that we want to get rid of liters NH3, and we want to get liters of hydrogen gas. We know that 2 liters of NH3 are produced from 3 liters of hydrogen gas. So multiply 5 times 3, 15, divide by 2, 7.5 liters of H2 gas would be required. Same thing with the other one. Start with 5 liters NH3 over 1 times, and then we know that we want to get rid of liters NH3, and we want to get liters of N2 gas. So, and we know that 1 liter of N2 gas is required to make 2 liters of NH3. So 5 times 1 divided by 2, or 2.5 liters of N2 gas would be required. And then depending on limiting reactants and things like that, say nitrogen is fairly inexpensive to get. Air is 78% nitrogen, so concentrating is a little easier than perhaps creating hydrogen. So maybe you want to make hydrogen the limiting reaction, so let's just use 2 times as much nitrogen gas, so 2 times as much, so we get 5 liters of nitrogen gas, and that makes hydrogen our limiting reactant. But so with Gay-Lussac's law, you can compare volumes of just gases, and this also works if the gases aren't the only thing in the equation. Let's take that. Let's do a combustion reaction. Let's do ethane plus oxygen. Or no, let's not use ethane. Let's use a heavier one. Let's do octane, C8H. Let's see, 6 times 2, 12, plus 6, 18. And we're going to make that a liquid. It's in liquid state. Plus O2 gas gives us incomplete combustion, carbon dioxide gas plus water in a gas form since it's hot. So go ahead and balance this. 8 carbons, 18 hydrogens, 2, so we need 9, 18 hydrogens. Now we've got 16 plus 9, 25. We got an odd, we got an even, so we actually want to double our oxygens. So that will double our hydrogens, which will double our carbons. And let's get all our oxygens together now. So we got 16 carbons, 36 hydrogens, 36 hydrogens. Now how many oxygens we got here? 18 plus another 32 is 40 oxygens. So we're going to need 40 here. So we're going to need 20 O2s. That should be balanced. Okay, so now let's say we want to control this reaction. How much oxygen will be need to produce, say if we wanted to produce 100 liters of carbon dioxide. Okay, so 100 liters of carbon dioxide, we know this calls for 16, so let's start with what we know. We got 100 liters of carbon dioxide we want to produce. Put that over 1 times, and then we're going to put liters of carbon dioxide on the bottom. That's what we want to get rid of, and we want liters of O2. And we know that 16 liters of carbon dioxide are produced from 20 liters of oxygen. So let's could probably do that in our head, but let's just make sure. 100 times 20 divided by 16 equals 125. Oops. We'll need 125 liters of O2 to get 100 liters of carbon dioxide. Now we couldn't take any of this and compare to it. How many moles of this would we need to make many liters of this? Because this is not a gas. Gay-Lussac's law can only work with gases, but you can compare gases inside of an equation even if they're not the only thing in the equation. The equation doesn't have to be all gases in order for Gay-Lussac's law to be applied. It's just we cannot apply it to anything other than a gas. Hope that makes sense for you. If not, drop me a line at mrc@mrcscience.com. Thanks.